In this video, I'll give a sketch of the proof of the primary decomposition theorem. So let's recall what the primary decomposition theorem says. At a high level, what it says is that every square matrix is similar to a block diagonal matrix, where the where the blocks can be taken in a very special way, and these are related to the minimal polynomial of the matrix, right? So formally speaking, given any linear transformation from V to V, so V could be Rn or Cn or in general any Fn, we can decompose the vector space into a direct sum of k subspaces, where each subspace is T invariant, and each subspace has the special property. It's not any arbitrary subspace, but it's a null space of pi raised to ri of t, and where the minimal polynomial of t can be p of x can be written as p1 raised to r1 times p2 raised to r2 all the way up to pk raised to rk. So essentially, if you can write the minimal polynomial as a product of k irreducible polynomials, or powers of irreducible polynomials, so each pi is irreducible, right, and monic, right? So it's irreducible in the sense that you cannot decompose it into a product of polynomials of smaller degrees, and it is monic. Then you can take vi to be the null space of pi raised to ri of t, and the vi's form a t invariant direct sum decomposition of the vector space, right? And to prove this, we'll need some properties of polynomials over a field. So we'll do a quick detour by studying some of the basic properties of polynomials. Since in this video we'll only use the properties that we need and we won't get into too much depth, so I won't prove everything over here, but at least most of this will be quite intuitive, because it's very similar to what happens for positive integers. Okay, so let me call p of x to be the set of all polynomials with coefficients from some field f, right? So think of f to be like the set of reals or the set of complex numbers. So the first question is, does p of x with standard addition and multiplication over polynomials, does this form a field, right? So I want you to pause the video for a minute and think about whether all the properties of a field are satisfied by the set of polynomials or not. Right, so these are the properties that a field must satisfy, right? Does the set of polynomials satisfy all of these properties? So is addition and multiplication of polynomials closed? Yes, it is. Is addition and multiplication commutative? Yes. Is it associative? Yes. Does there exist an identity element? Yeah, the zero polynomial is the identity element. What about the multiplicative identity? 1 is the multiplicative identity, right? So this basically comes from the field, right? And so does there exist an additive inverse for every element? Yes, because if you have p of x, then minus p of x, which is obtained by changing the sign of each of the coefficients of the polynomial, this is also a valid polynomial and forms the additive inverse, right? What about the multiplicative inverse? So this is where a property is not satisfied. So not every polynomial has a multiplicative inverse. For example, if you take the polynomial x, certainly 1 by x is not a valid polynomial, and therefore a multiplicative inverse does not exist, right? But it is certainly distributive. So it satisfies, so the set of polynomials satisfies all the properties of a field except for the existence of a multiplicative inverse. And such an object, such a set, which satisfies all the properties of a field except for existence of multiplicative inverse, is called a commutative ring. So p of x equipped with addition and multiplication of polynomials is a commutative ring. Now, a general ring satisfies everything else except for commutativity, right? So in general, a ring may or may not satisfy commutativity, but certainly the set of polynomials satisfies commutative property, and therefore is what we call a commutative ring, right? So another example of a commutative ring, apart from the set of polynomials, is the set of integers, right? So the set of integers with standard integer addition and integer multiplication is also a commutative ring. And many of the properties that hold for the set of integers also holds for the set of polynomials. And in particular, the notion that we will use is what is called irreducibility of a polynomial. So a polynomial is said to be irreducible if you cannot factor it as a product of two polynomials of degree greater than or equal to 1. So for example, if you take f, the field, the coefficients come from the set of reals, then certainly every degree 1 polynomial is irreducible. So x plus 2, 2x plus 5, and so on, these are irreducible polynomials because you cannot factorize them as a product of smaller polynomials of degree greater than or equal to 1, right? And another non-trivial example, so if the coefficients come from the set of reals, then can you give me an example of an irreducible polynomial of degree 2? So this is a polynomial of degree 2 which is irreducible because over the reals you cannot factorize x squared plus 1, right? So, but on the other hand, if the field had been a set of complex numbers, then if the coefficients are allowed to be complex, then this can be factorized as x plus I times x minus I, right? So over the field of complex numbers, that is, if the coefficients are allowed to be complex, then how do you characterize can you characterize the set of all irreducible polynomials with coefficients from C? So what is the set of irreducible polynomials of the ring P of X with coefficients from C? So this is just the set of degree 1 polynomials, right? So this notion of irreducibility is something that is quite familiar to you. So if you look at the set of integers, can you think of a similar concept, a concept similar to irreducibility in the set of integers? So certainly the concept of a prime number is similar to the concept of irreducibility, right? Because a prime number, so of course prime numbers are obviously integers. A prime number is one which cannot be expressed as a product of two smaller integers not equal to 1, right? So non-unit integers, right? And essentially the idea of an irreducible polynomial is a generalization of the concept of prime numbers, right? And similarly, just as we have the greatest common divisor of a set of integers, we'll define the greatest common divisor as a set of polynomials as the highest degree monic polynomial which divides each of the polynomials p1, p2 up to pk. Right? So for example, if we have the following, so find the GCD of the following polynomials with coefficients from R. So let's say x square minus 2, or let's say x square minus 4 and x square minus 5x plus 6. Right? So find the GCD of these two polynomials. Right? These where coefficients come from R. Okay, so the main concept or main property of polynomials that we will require to prove the primary decomposition theorem is the following. So if we have a set of polynomials p1, p2 up to pk whose GCD is equal to 1, then we can find some other polynomials q1, q2 up to qk, so k other polynomials such that p1 q1 plus p2 q2 and so on all the way up to pk qk, this is equal to 1. Right? And this property holds for integers as well. So if we have a set of integers a1, a2 up to ak whose GCD is equal to 1, then you can find other integers b1, b2 up to bk such that a1, b1 plus a2, b2 all the way up to ak, bk is equal to 1. This is a key. This is a very important number theoretic property, and we'll basically be using this number theoretic property to prove the primary decomposition theorem. Alright, so let me quickly go through the proof. So what do we want to show? So suppose that the minimal polynomial of t is p of x, which is p1 raised to r1 times p2 raised to r2 all the way up to pk raised to rk. Note that each pi is an irreducible polynomial. If I define vi as a null space of pi raised to ri of t, then the following two properties hold. So each vi is t invariant, and the vi's essentially form a t invariant direct sum decomposition of v, the subspace of the vector space v. Right? And how do we prove this? So we prove it in the following way. So let's suppose that I want to prove the first property, right? That v is a direct sum of the vi's. Right? So in order to do this, I'll define the following polynomial f1, f2 up to fk. I'll define k polynomials where each fi is the minimal polynomial p of x divided by pi raised to ri of x. Right? So in other words, this is equal to the product over all j going from 1, 2, 3 up to n up to k, but j not equal to I of pi pj raised to rj of x. So for example, if I had p of x to be equal to x square plus 1 the whole square times x minus 2 times x plus 5, suppose that this were the minimal polynomial, then f1 would be x minus 2 times x plus 5, f2 of x would be x square plus 1 the whole square times x plus 5, and f3 would be x square plus 1 the whole square times x minus 2. Right? So these would be the f1, f2 and f3. Now the way I've defined it, you should be able to easily convince yourself that the fi's have GCD equal to 1. right? The GCD of f1, f2 up to fk. So this is in fact equal to 1. Okay, and why is this the case? If the GCD were something which, if it were some polynomial not equal to so if it's some polynomial of degree greater than or equal to 1, then there should be some term which divides each of the FIs. But each of the FIs is missing one of the PIs, precisely one of the PIs, right? And each of the PIs is irreducible, and therefore the FIs have GCD equal to 1. So even if you look at this particular example over here, so clearly x plus 5 can, so the only factors of the FIs are x square plus 1 or x minus 2 or x plus 5, right? You can't have any other factors. And certainly x square plus 1 does not divide f1, x minus 2 does not divide f2, and x plus 5 does not divide f3. So there is no polynomial, no non-trivial polynomial which divides each of the FIs, right? And therefore the GCD is equal to 1. Now since the GCD is equal to 1, you can find polynomials g1, g2 up to gk such that f1 of x g1 of x plus f2 of x g2 of x, so on fk of x gk of x is equal to 1, right? And in particular, since these are polynomials, we have f1 of t g1 of t plus f2 of t g2 of t all the way up to fk of t gk of t to be equal to the identity matrix, right? So this is going to be and moreover, if you look at f1 f2, you can prove that p always divides f1 f2, and in particular the minimal polynomial divides fi of x fj of x as long as I is not equal to j, right? So in particular, if you look at this example over here, let's take f1 f2. This is x minus 2 times x plus 5 times x square plus 1 the whole squared times x plus 5, right? So clearly this is p of x, and therefore p of x divides f1 f2. Similarly, you can show this for f1 f2 f2 f3 and f1 f3, right? So for any I not equal to j, p of x divides fi of x times fj of x, and what this implies is that f I of t fj of t is equal to the 0 matrix, and also that fi of t gi of t fj of t gj of t is equal to 0, right? Now if I define ei to be fi of t gi of t, then from this property and this property I have that e1 plus e2 so on up to ek is equal to the identity matrix, and ei ej is equal to the 0 matrix for I not equal to j, right? So if I take each of these EIs as my projections, then this certainly gives me a direct sum decomposition. But what are these projections in fact equal to, it turns out that these are the projections corresponding to each Vi. So the projection onto Vi turns out to be Ei. It requires a little bit of work, but you can show that the projection is in fact equal to Ei, and these Eis have the property that E1 plus E2 up to Ek is equal to I, and Ei Ej equal to 0, and this proves that the V can be written as a direct sum decomposition of the Vi's, right? So that was the first part of the theorem, right? That V can be written as a direct sum of these subspaces. But what we also want to show is that each Vi is T invariant, right? So if Vi is the null space of Pi raised to Ri of T, then each Vi is also T invariant. And the reason why this is true is because now take any vector V which is in Vi, right? What we want to show is that TV is also in Vi, right? So TV is in Vi only if TV is also in the null space of Pi raised to Ri of T. So let's look at Pi raised to Ri of T times TV, right? Now using the associativity property, this is Pi raised to Ri of T times T of V, right? But this is after all just a polynomial, right? It's a polynomial, it's a matrix polynomial, and this is also another matrix polynomial. Therefore this is also equal to T times Pi raised to Ri of T times V, right? So now if you look at this particular term that I have over here, V is already in the null space of Pi raised to Ri because it's in Vi, right? So this should be equal to 0. So I have T times the 0 vector which is equal to 0, right? So this implies that T times V is also in Vi, and therefore each Vi is T invariant, right? So this completes sort of a proof, a very basic proof of the primary decomposition theorem. So overall what we've shown is that although not every matrix is diagonalizable, every matrix is certainly similar to a block diagonal matrix, and each block corresponds to a T invariant subspace. So if for example you're dealing with the vector space Cn, then each of the Vi's corresponds to the null space of T minus lambda I raised to some Ri, right? But on the other hand, if the field is, say, the set of reals, and maybe one of the terms in the minimal polynomial is say x squared plus 1, then certainly one of the subspaces Vi would be like a square, or this example we are dealing with T, so T square plus I, so null space. So the Vi's could take the form, say, null space of T square plus I.